Okay, everybody, we're going to start our first lesson in physics. I don't know if we're always going to do the flip or if even anybody's going to listen to this one, but I already went over the lesson once, so I'm going to go over it again for myself. And I thought if I'm going to go over it again, I may as well record it. Please pause the video, read through the objectives for this particular lesson that we're going to get through. The very first lesson is motion along just a straight line. And to begin our studies, we're going to first study the topic of kinematics. Now, kinematics pretty just means that there's motion going on. Eventually, we'll talk about different types of energy, and we'll have kinetic energy versus potential energy, and that kinetic energy deals with motion. But kinematics, by definition, is the classification and comparison of motion. All right. In every situation that we initially talk about, we are going to follow these general restrictions. The first general restriction is the motion today is along a straight line only. And as you write that down, think about what that would mean. This line may be horizontal, vertical, or diagonal.
Where do you want it to go where?
Okay. The second thing we're going to have on our restrictions is that there's forces, a push or a pull, cause motion. And the third thing is the moving piece is a particle. So whatever we happen to be talking about. Or behaves like a particle. All particles move at the same rate. So whatever we're talking about, a car, a person, we're going to assume, first of all, we're going to kind of treat it like it's its own particle and that all the particles in that object are moving at the same rate. Okay. The next thing is position and displacement. So the first thing we'll talk about is this origin. It's always the reference point, and it's normally 0. So we'll say reference point, and then we'll write normally 0. And then we have the positive direction, which is to the right of the origin. Missed an I. And then we have the negative direction, which is to the left of the origin. Okay, so right here, we would consider that the origin. Oh, I spelled it wrong. And then this would be negative, and this way would be positive. So that's probably no surprise to you. All right, let's take a look at page 2. So I feel like the first page is kind of self-explanatory. Let's move on and turn the light on, see if that's helpful at all. Okay. Example 1. A particle is given to be at x1, which means position number 1, at -5 meters at time 0. So if you notice, if you've never seen these before, those are that's sub 1, like x sub 1, t sub 1. That means at like spot 1 or like the initial, or at least what they're calling 1. And then here's the second one and the second one. So x sub 2 is 6, t sub 2 is 4. Interpret each of these positions with respect to the origin. So x sub 1 is 5 meters to the left of the origin because it's negative. and x sub 2 is 6 meters to the right of the origin. Okay. The ability to describe the position of an object allows us to ask questions about the change. With this change comes two different types of quantities. There's vectors. Vectors have magnitude and direction. Scalars only have magnitude. The distance of something is the full path an object travels. The full path an object travels. And displacement is a change in position from x sub 1 to x sub 2. Oh, I missed from. I didn't even write from. I wrote for. There you go, from. Okay. So displacement has its own little formula. That's called delta x. That means change in x. And you take the second position, x sub 2, and you subtract the first position, x sub 1. Again, that little triangle thing is called delta, and it means change. Okay? So we are going to take a look at example 2. Calculate the distance and the displacement for a trip from your friend's house to the grocery store and then to your house. Let's do A. Let's see, where would be, I like all this area over here. So A. A is the distance. And our final answer is going to be 10.7. So let's take a look as why the distance, it will equal 10.7. Let's go ahead and work that out, okay? So I have my answer key beside me. The answer is 10.7 miles, and let's explain why. So the distance, we're going to go from your friend's house. So here's your friend's house at 0. And we're going to go to the grocery store. And then to your house. Okay? So we have a trip from your friend's house to the grocery store and then to your house. So here's your friend's house. We're going to go all the way to the grocery store, which is 4.3 miles away. And then we're going to go back to your house. Okay? Which is, a little more than that, huh? We're going to start at your friend's house. We're going to go all the way to the grocery store. So we're going to have to go this whole distance here. And we're going to go back to your house. So all together, that's from your friend's house to the grocery store. So it's 2.1, 4.3. We're going to add some more. And then we're going to go back to your house. So we have another 4.3 to go back. And sure enough, if you add 2.1 and 4.3 and 4.3, you get 10.7. So let's take a look at option B. Option B is the displacement. So it's kind of like how much your overall change is. So that's the one where you're just going to do change of x equals x2 minus x1. So that's like your final position. So your final position is your house, right? So that's 2.1 minus your original position. Your original position was at your house, so minus 0. So the displacement is actually 2.1 miles. And if it kind of makes, I hope it makes sense because like this is where you're starting, this is where you're ending, so you're only 2.1 away. It doesn't matter that you've gone back and forth. Displacement talks about where you started from where you ended, and this was in the positive direction. Okay. Let's talk about average velocity and average speed, but we're going to do that on the next page. I think maybe we should have put that on the next page, but let's read about it down here first. Once we can describe motion, we want to consider how rapidly an object moves. So our nice little equation here is average speed. So average speed is the total distance so how far we go all together, that's distance, notice not displacement, over the change in time. So please circle the word speed and please circle the word distance. Those are how those are related. Now, if we wanted to make kind of a little equation up here, that's S, average, equals D for distance, I'll even write distance if you want, over t, change in time. If you ever needed to solve for one of these other letters, hopefully you know that if you needed to solve for distance, you could just move that t to the other side, so you do speed times time. And if you wanted to solve for time, you could just move that s over. So time is distance over speed. And remember, that's average speed. Okay? So it's nice that you can get 3 equations from one equation. Example number 3. And being able to manipulate equations like this is very important in this class. Example 3. A kingfisher is a bird that catches fish by plunging into the water from a height several meters. If a kingfisher dives from 7 meters in the air up here with an average speed of 4 meters per second, how long does it take to reach the water? Well, because we made these cute little equations up here, it's asking for time. So here, let's label some stuff. We know that we have the speed, and the speed is 4 meters per second. And we also know that we have the distance that it travels. The distance is 7 meters. So if we want to solve for the time, we can do that. So we'll write time equals distance over speed, which is 7 over 4. And we can include our units if you want to. They'll all cancel and you'll just get seconds overall. That ends up being 1.8 seconds. So I use this formula, which came from here. In many situations, there's a quantity that's even more useful than average speed. It's average velocity. Average velocity is the ratio of the displacement to the change in time. So hopefully here the word velocity is with displacement. So average velocity, we're going to do delta x, which we know is displacement, over delta t. Maybe we even want to write displacement here, so you know that means displacement. I can spell, it's okay. To change in time. So see how the word displacement relates to velocity, whereas distance relates to speed. So that's going to end up being x2 minus x1 over t2 minus t1, okay, which is the same as delta t and delta x. Let's take a look at example 4. An athlete sprints 50 meters in 8 seconds. They stop, and then they walk slowly back to the starting line in 40 seconds. If the sprint direction is taken to be positive, what's the average sprint velocity, the average walking velocity, and the average velocity for the complete round trip? So let's talk about A. A is the sprint velocity. Now, if you ever watch me do my homework, I always kind of draw this out. So we have, here's our athlete. They sprint 50 meters. They stop. So they go this way at first, and then they slowly walk back that way. So it kind of helps me just to have a visual. And I'd probably write like 50 meters here. Okay. I can write 8 seconds for this way, and I can write 40 seconds for this way. That helps me to visualize it. All right, so part A, the sprint velocity, well, that happens from time 1 of 0 to time 2 of 8. Okay? And that also happens from x1 of 0 to x2 of 50. So the average velocity for this particular section is 50 minus 0. Hopefully you're seeing connection to algebra and slope, which turns out to be 50 over 8, which is simply 6.25 meters per second. Part B asks about the average velocity for the walking. So I'm going to do walking. Okay, and I am going to stop the video because it's just about to cut me off, and then I'll come back.